Okay, so this is still 2.2 out of Griffith's quantum mechanics, where we're talking about the infinite square well. And in the last video, we solved the time-independent Schrodinger equation and got these sets of solutions. So n here, is a natural number. So we actually have infinitely many sets. 1, 2, 3, so on and so forth. So we have our sets of solutions here, and there's a few things we want to discuss about the solution. Okay? So the first thing is psi sub 1. In other words, when n equals 1, this is called our ground state. Some people will think that this should be your ground state when n equals 0, but you just get the trivial wave function at that point. So that is not our ground state. This is our ground state. And then psi sub 2 is called our first excited state. And psi sub 3 would be your second excited state, so on and so forth. So just kind of wanted to get some of that terminology out of the way. And now, if we look over here at these graphs that we have, these are a few of our wave functions. So psi 1, psi 2, psi 3. This is your ground. This is the first excited state. This is the second excited state. And it goes on and on and on. Okay? So there's a few properties that are worth talking about before we continue. The first one is graphically, if you look at this, if you were to draw a line, let's just draw like a vertical line at x equals a over 2. This is x equals a over 2. Trying to draw it well. You'll see that the function goes from even to odd and then back to even. So it alternates. Okay? And this is because of the symmetry of our potential. And anytime you have any sort of potential function that's symmetric, you're going to have this property, including with the infinite square well. Okay, so that's the first one. The next thing we want to talk about are the nodes. So the nodes are the points where your graph crosses your x-axis. So there's a node here, there's a node here, there's a node here. There's no nodes on the ground state. And you might say, well, what about here and here? It doesn't really cross there. It more so, try to get rid of that. It more so just touches. Those are the boundary areas. The nodes, though, you can see it actually goes through and ends up on the other side. And maybe you see the pattern here. We start off with 0 nodes, and then 1 node, and then 2 nodes. And you can imagine if you keep going and going and going, you'll get more and more nodes. So each time you go up from an excited state, you get one more node. Okay, cool. The next one, maybe not obvious by looking at the graph, but it's worth working out here, is that all of your psi's are what we call mutually orthogonal. Which mathematically we just say as the integral of psi star x, the mth state, multiplied by the nth state, dx, is equal to 0. So this is kind of like your inner product, and just like how your dot product When it's equal to 0, it can tell you when you have perpendicular vectors. This is kind of similar. This is just our inner product, if you're familiar with that. Something we'll talk about in a later chapter. But anyways, this is true so long as m is not equal to n. That means you're taking two different states. And just real quick, you might say, hey, our wave function up here, there's no imaginary component to it. It's real entirely. And that's true, but this idea of our states being mutually orthogonal, it's going to be a reoccurring theme, or it will be something that pops up again. So I'm going to write this generally, and then hopefully when we get to it in later sections, it'll kind of go smoothly. So it's worth actually proving this section. It's not too bad. That the integral of psi at state m times psi n dx, well, what is that? Well, each term will have the root 2 over a, so we'll have just 2 over a. The integral from 0 to a, sine of m pi over ax times sine of n pi over ax dx. Okay, so this is the integral that we want to compute. Okay? Alright, so there's a few ways you can do this. One, do I have it handy over here? Sometimes I write down handy little trig equations, but I could look it up really quick. Just edit this part out. Okay, so this is just a trigonometric identity. Sine of x times sine of y is equal to cosine of x minus y minus cosine of x plus y, all divided by 2. Okay? So I'll just pull out that 2. We have 1 over a, the integral from 0 to a, cosine of m minus n over a pi times x minus cosine of m plus n over a pi x. Okay, so we can just do these two integrals separately. And what do we get? Well, you'll have a u substitution here. So you'll have an a over m minus n, a over, and there's a pi down here, a over m plus n pi, and then sine of these functions. So the a will cancel out over here, and we just get 1 over m minus n times pi. The cosine turns to a sine. M minus n over a pi x. And then minus 1 over m plus n sine of m plus n over a pi x. And these are all evaluated from 0 to a. Okay, so that's a u substitution integral, basically, 2 of them. Okay? Alrighty, so let's see. If we were to evaluate this, say we plug in a, well, you're going to get sine of m minus n times pi minus, we have the stuff up front, but it's not actually going to matter, m plus n times pi. Remember, m and n are elements of The natural number is the set of natural numbers. And if you add or subtract two natural numbers, you're just going to get another natural number because there's closure in that set. So sine of a natural number times pi is always going to be 0. And obviously if you plug in 0 for x, you're going to get 0. So this whole thing is equal to 0, which is what we wanted to show. Now you might notice right here, if m equal to n, remember one of our stipulations was that m cannot equal n. If m equals n, well, you're going to be dividing by 0. So that is one area where we cannot do that. But that's okay because there's a different way we can approach that. If m equals n, then you just have the integral of, so I'll have your 2 over a sine squared of, we'll just call it n pi over a x dx. And again, you can do this with the u substitution. Let's see, this will be 2a times 1 over 2 times what? A over n pi. Let's just do the u sub instead of trying to guess it. So this is all squared. So that's 2 over a. Let's do this. So this is the same thing as the integral from 0 to a. These are our bounds. Of 1 minus cosine of 2 times n pi over ax all over 2 dx. So the 2 comes out, cancels, fantastic. So we have 1 over a times the integral of from 0 to a dx minus the integral from 0 to a cosine of 2n pi over ax dx. Obviously this is going to be a, so we have 1 over a times a minus, this will be a over 2n pi sine of 2n pi over ax, should stay positive I think. And then we're going to evaluate this from 0 to a. And once again, when we do this, sine of 0 is obviously 0. If we plug in a for x, you're going to have sine of 2n pi. This is going to be 0. So we have 1 over a times a minus 0, which, lo and behold, is just 1. So then we can actually write our integral, the inner product of these two states, as what we call the Kronecker delta. So the Kronecker delta is something that kind of pops up a lot in physics. The Kronecker delta is equal to 0 if m is not equal to n, and 1 if m is equal to n. So that's what we just showed. If m equals n, you get 1, and if they're not equal, you get 0. Awesome. Okay, almost done here. The next thing that's mentioned we'll talk about is that they're complete, which is to say any function you can imagine, so long as it's actually a function, can be comprised as a sum, as a linear combination of our state psi sub n. Which is to say, as we know what that is, I'm just going to plug in for psi. C sub n, psi sub n pi over ax. So this, the fact that this is true, it's obviously not necessarily obvious unless you're familiar with this. This is a Fourier series. So if you've seen it before, then it kind of jumps out out at you, but essentially any function that you want to describe, you can describe as some sort of linear combination here of our states. Okay, so that's when we say complete, that's essentially what they mean. And the reason why this is helpful is something called the Fourier trick. So just focus on these two parts of the inequality. If I multiply both sides by some state psi m times f of x, that's equal to this sum. Now obviously that's a different state, but I'll just put it here. It's a constant. These are functions of x. And now you can integrate this and take advantage of some properties. So first off, this property. We're going to rewrite this just a little bit, but hopefully you can see what we're getting. The integral of this state times any function that we imagine, we'll see what that function is here in a little bit, is equal to, the summation can come outside of the integral, so this is just linearity. C sub n is not a function of x, so that can come out no problem. And then we have psi sub m star, psi sub n, they're both functions of x, dx. But we just said that this is the Kronecker delta. Okay? So then this integral of one of our states times any function is equal to the summation from n equals 1 to infinity of c sub n, the Kronecker delta. So we're summing over all these different terms, but remember the Kronecker delta is 0 everywhere. So you're basically adding a whole bunch of zeros except for one term, c sub n, which is the same thing as c sub n, because n equals m, that's where our Kronecker delta equals 1. So then, you can rewrite this integral, should have been a dx there, it's okay. It's going to be 0 plus 0 plus 0 plus 0 plus c sub m. Okay? So any constant, call it c sub n, any one of our weighted constants can be expressed this way. Okay? Awesome. Now, we're going to work towards why we actually did this. It's not just a cool math property, it's going to be useful for us. Our entire wave function, which remember is a function of x and t, is our time independent part. That's our lowercase psi. But then we have to multiply this time dependence, which is e to the minus I e sub n t over h bar, I think it was. And then remember what e sub n is. We defined that in the previous video as n squared pi squared h bar squared over 2m a squared. So we already know what that is. So then our entire wave function is just the square root of 2 over a, our normalization constant, sine of n pi over a x, e to the minus I n squared pi squared, there's h bar squared here, over 2m a squared times t. I think there was not an h bar there. I think it was just this. Okay? And then our most general solution would be a sum of all the possible solutions. So just like how we add our different solutions for a differential equation, we're doing that here, only it's an infinite sum now, because there's infinitely many solutions. Okay. Okay. And if we look at when t is equal to 0, this is kind of like our initial condition. This is just equal to 1. And then, of course, this is just psi sub n of x. So this is equal to the sum equals 1 to infinity c sub n psi sub n of x. Well, this looks an awfully lot like what we were doing before, where this is some general function f of x, right? What we were doing up here. So if we wanted to find these coefficients c sub n, we could follow that same pattern. We just integrate from 0 to a. There's our normalization constant out front. Psi sub n pi over ax times our wave function. That's like your regular function. And then our psi sub m, or n because of the way our Kronecker delta does. And there you go. That's how you can get your c sub n's from that. I'm going to stop right there. In the next video, I'm going to go through some problems, and I'm going to complete the infinite square well section. So if you like this video, if it's helpful, please like and subscribe. I'm trying to grow my channel. I'd really appreciate it, and I'll upload more. Thank you.